We continue with chapter 6, determinants. This will be a very brief summary of this chapter. And the reason for the briefness is the following. First of all, there are some theoretical applications and generalization of determinants in pure mathematics. What happens in practice is that Gaussian elimination is used, which is the forward part of the Gauss-Jordan elimination, to calculate determinants. So this is basically solving a linear system of equations, at least halfway, the forward part, in order to calculate determinants, and not the other way around. We don't really use determinants to calculate the solution of linear systems. So we don't really use the textbook in this chapter. What I would like to refer to is the undergraduate textbook online. The title is A First Course in Linear Algebra. This is by Robert A. Beezer, and the website is linear.ups.edu. So we will go through the basic properties and the definition, and we will also look at the Gaussian elimination for determinants. Some definitions. First of all, suppose A is an n by n matrix, then the submatrix denoted by A, parenthesis I, vertical sign J. There are some other notations for this. This is what this undergraduate textbook I am referring to is using. So this Aij submatrix of A is the m-1 by n-1 matrix obtained from A by removing row I and column J. All right, so the idea is that if you have an A matrix, it has an ith row and a jth column, and then when you delete this, you get a smaller matrix, one row less and one column less. So using this, the next definition is that suppose that A is an n by n square matrix, so same number of rows as columns, this is now important, then the determinant of A is denoted by det of A, or sometimes the absolute value notation is used for the A, and it is calculated as in the first case, if the size n is 1, we have a 1 by 1 matrix, then the determinant of A is just this 1 entry, which is one number, and that's actually the same as the matrix itself. Second case, if n is greater than or equal to 2, then the determinant of A is calculated as the sum I going from 1 to n minus 1 to the I plus 1 times A1I entry times the determinant of A1I when we remove the first row and the ith column. So we can expand this sum, and what we get is that we have the 1 entry A11 multiplying the determinant of a submatrix that we get if you remove the first row and the first column. Then the second term has a negative entry since we have alternating sign here. So minus, and the second term is when I is 2. So this is the first row and the second column entry times the determinant of the submatrix that we get by removing the first row and then the second column. And so on. We continue this with alternating sign, and the last entry has minus 1 to the n plus 1 coefficient, which is either positive or negative depending whether n is odd or even. And then the 1n entry times the determinant of the submatrix that we get by removing the first row and the nth column. So this is called a recursive definition, because for the case n, what we need is n minus 1 by n minus 1 matrices. So for case n, we need case n minus 1, which in turn needs case n minus 2, and so on. So one by one, we're supposed to go down all the way into case 1, or case n equals to 1, which is the only explicit formula finally. But until we reach n equals to 1, we have to go back step by step from n to n minus 1 and n minus 2 and so on, sub matrices. There are a lot of properties. We will use some of them. For n equals to 1, we have that A is just a matrix, and then the determinant of the matrix is just the number itself. For n equals to 2, we have A equals A, B, C, D with some entries, a 2 by 2 matrix, and then its determinant is A times D minus B times C, which is a kind of cross multiplication with the second one with negative sign, the second term. Another property is that any row or any column can be used to expand the determinant, and we can exploit this sometimes. For example, if you have to calculate the determinant of 3 by 3 matrix 3, 2, 5, 1, 0, 0, 7, 6, and 4, then these entries, depending on where you start expanding it. In fact, this definition was using the first row entries, and there it had alternating sign, plus, minus, plus, minus. So we had these plus, minus, plus signs, but if instead of the first row we use the second row, then the alternating sign would continue. So plus, minus, plus, and then this is minus, this is plus, and this is minus, then again plus, minus, plus. So there is alternating sign everywhere. And then since there are these 0 entries, it's better to use that row with the most zeros in it, because then what we get is that using the sign minus and then the entry 1, it has to be multiplied with the determinant of a 2 by 2 matrix that we get by deleting this row and this column. So then we are left with matrix 2, 5, 6, 4. And then continuing with this row, with the second row, we would have plus 0 times sum 2 by 2 determinant minus 0 times 2 by 2 determinant, but we don't really care what those determinants are since they are multiplied by 0. These cancel out. And in fact, we just have to calculate one submatrix determinant. So this will be minus, and then the cross multiplication 2 times 4 minus 5 times 6. This is 8 minus 30. This is minus 22, so this is plus 22. So using a lot of zeros, we can shorten the calculations. Some other properties, for example, the transpose matrix has the same determinant as the original matrix. Then another property that multiplying a row with a scalar C results in the determinant getting multiplied by C. Also, adding 2 rows of A together, adding rows of A, leaves the determinant unchanged. And for example, for triangular matrix A, the determinant of the matrix is just the product of the diagonal entries. These 3 properties will be used later for calculating the determinant. Some other properties, if you multiply together 2 matrices, A and B, the determinant of the product is the same as the product of the determinants. Also, A is non-singular, which means that invertible, if and only if the determinant is not 0. We will not use it, but I should mention maybe that if the determinant of A is very small, that's how we denote it, but much smaller than 1, and maybe in absolute value, because the determinant can be positive or negative, then A is so-called air-conditioned. So this means that you can expect in numerical calculations a lot of errors due to rounding errors and division by numbers that are close to zero, overflow errors. In general, if you look at how the 2x2 determinant is calculated, for example, with entries A, B, C, D, this is AD minus BC. If you calculate the number of operations that we have to use, we have one multiplication, another multiplication, and then a difference of two terms. So this means 3 operations. Then if you look at the determinant calculation for 3x3 matrix, what we get is that this is A times the determinant of EF HI minus B times the determinant of DF GI plus C times the determinant DE GH if we use the first row to expand, for example. So first we have 3 times the calculation of 2x2 determinants, which is 3 operations, and then we have also multiplication in each of these cases, so it's plus 1, and then we also have a difference and addition, so this is plus 2. Altogether this is 14 operations. Then if you try to do the same thing for a 4x4 matrix, you can see a pattern here. So we have 4 sub-determinants. Each of them will be calculated with 14 operations, and then we have the multiplication of each of them with the coefficients. And then we have 3 addition or subtractions of the 4 terms. So if you calculate what this is 15 times 4, this is 63. That's already a lot of operations. If you try to calculate the number of operations for 5x5, you see that we have then 5 submatrices. Each of them will take 63 operations to calculate. Then each of these subdeterminants have to be calculated, multiplied by their coefficient, and then plus 4 addition or subtraction. So this is 64 times 5, that's already 324. So this increases quite fast. This is used in numerical calculations. The factorial notation is used, and big O notation is used for the rough estimate of the number of operations. And n factorial grows very, very fast as n increases. In fact, if you compare this to n factorial, 4 factorial is only 24, so 63 is more than that. 5 factorial is only 120, so again we have that this is actually underestimating with the n factorial. So this is very, very costly. This is called a naive calculation, very costly. What this means is that, for example, Cramer's rule, you can look up what Cramer's rule is. This is a formula to calculate the solution of a linear system using determinant. It makes no sense in practice, computationally, for large matrices. And in practice, we have huge matrices, like 1000 by 1000 size matrices. I should mention that still there are theoretical uses of determinants and important theoretical applications. By theoretical applications, I mean applications in pure mathematics. And on Blackboard, I made some notes on some special equations that you can look up in differential geometry, for example. Much faster than the definition is to use Gaussian elimination or forward elimination. What I'm going to discuss here is the modified version using least common multiples. So in the homework assignments, usually we use integers. If you look at how the determinant is calculated, it's just multiplication, addition, and subtraction. So you see that for matrices with integer entries, the result should be always integer. But if you start doing Gaussian elimination, you encounter usually fractions. And it's kind of painful to do this by hand calculating with fractions. And it turns out using least common multiples, you can avoid that to avoid fractions. Of course, cannot avoid fractions in practice. Decimal numbers are unavoidable. So here we use the elementary row operations that we discussed here. Some of them are changing the values of the determinant, like multiplying a row by C scalar, it multiplies the determinant. And some other, like adding rows together, don't change the determinant. So the idea is that we start with the matrix A, then we do elementary row operations to get echelon form. Not reduced echelon form. In fact, it wouldn't make sense to work hard for the reduced one, because that would be the identity matrix. Since if the determinant is not 0, we're supposed to have an invertible matrix, and then the reduced row echelon form of a non-singular matrix is the identity matrix. So just an echelon form, and then this is supposed to be the echelon form will be the upper triangular. And for upper triangular matrices, all we have to do is multiply together the diagonal entries. So example, if we have a 3 by 3 matrix with entries, for example, 4, 7, 8, 2, 3, 6, 5, 7, -2. This 4 is the first pivot entry. Then for row 2, again, let me emphasize that I'm going to use least common multiples to avoid fractions. You don't have to do that, but then you have to work with fractions, and then the result is a little bit different depending on how you do the multiplications. So the least common multiple for row and 2, we use the 4 and 2. So the least common multiple of 4 and 2 is 4. So the idea is that I just get the least common multiple with opposite signs. So I multiply the second row by 2, and I get 4, and then what I have to do is subtract just 1 times the first row. For the third row, the least common multiple of 4 and 5 that I will use, least common multiple of 4 and 5, that's 20. So I multiply row 3 by 4 and subtract from this 5 times row 1. Then what I get is the first row doesn't change. Then I get 0. 6 minus 7 is -1. 12 minus 8 is 4. Then the second row is done. And the third row, 4 times 5 is 20 minus 20. Then 4 times 7, 28 minus 35. That's minus 7. Then 4 times -2 is -8. And minus 5 times 8, 40. So it's -48. Then continue with the next pivot, the second row, -1. And then row 3, the least common multiple of -1 and -7 is 7, or -7. Well, it's up to you what kind of signs you use. For example, what I can do, maybe the simplest way to do it is just use 1 times row 3 without changing its sign. And then what I have to do is multiply the second row with -7 to get +7. So that makes the 3-2 entry 0. So I get -7 + 7, 0. Then I get -48 and -28. That's -76. So now I have an upper triangular matrix, and for that all I need is the product of the diagonals. 4 times -1 times -76. Except I have to make some corrections, because I multiply the second row with 2 here, multiply the third row with 4, and then here I multiply the third row with 1. So I have to divide with those numbers, because those multiplications change the determinant, multiply the determinant by 2, 4, and 1. So I'm now correcting for those multiplication by dividing through with them. And then there is some simplification. Minus times minus is plus. 76 over 2 is 38. This is the determinant. So the main steps are do a Gauss elimination, the forward one, while we are going downward to make zeros under the diagonal entries, step by step, using least common multipliers. I avoid using fractions because those are prone to errors if you do that by hand, and also it takes longer to calculate with fractions than with integers. Once we get a diagonal matrix, its determinant is just the product of the diagonal entries, and in these steps we multiply with some numbers the rows. When we are subtracting 5 times row 1, you don't have to worry about it. What you have to worry about is that for row 3 we multiplied by 4, for row 2 we multiplied row 2 by 2, and then again we multiplied row 3, but that was actually 1, so that didn't really change anything. And we have to divide, we have to compensate for those multiplication with division. So this is the way to calculate in more efficient way. Maybe not for 3 by 3 matrices, but for larger matrices it's more efficient than the definition. And this is a modified version of the method. That's the whole chapter we're gonna cover. And the only reason we really cover determinants because these are needed for the next step to calculate eigenvalues. Ironically, in practice, even for eigenvalues, determinants are not useful, but we have to do these calculations by hand, and we have to know the theory of the eigenvalues, so we need the theory of determinants also.